These are the answers to the AP Chemistry packet on topics 4.5 and 4.6. This is MCQ Practice, which means these are multiple choice questions for you to practice so you can prepare for the AP Chemistry exam. In the video description area, there is a link to the packet that accompanies this video. Now, let's take a look at our first multiple choice question. Question 1 says, in a certain experiment, a 48.0 gram sample of CS2 reacts completely with Cl2 in a chemical reaction according to the equation shown above. What is the minimum mass of Cl2 consumed in this experiment? So the strategy for solving this problem is to convert grams of one chemical into grams of another chemical. So first, we're going to use the molar mass of CS2 to convert grams of CS2 into moles of CS2. Using the information on the periodic table, the molar mass of CS2 is equal to 76.13 grams per mole. So we'll start with 48.0 grams of CS2, and we'll use a conversion factor to convert from grams into moles. Now we'll use the coefficients in the balanced chemical equation to convert moles of CS2 into moles of Cl2. And based on the coefficients, we see that there are 3 moles of Cl2 consumed for every 1 mole of CS2. So that's our next conversion factor. Finally, we'll use the molar mass of Cl2 from the information on the periodic table to convert moles of Cl2 into grams of Cl2. And that gives us, from the periodic table, a molar mass of 70.9 grams per mole. So now all we have to do is pick up our calculator, and we'll start from left to right. 48 divided by 76.13 times 3 times 70.9, and that gives us an answer of 134 grams of Cl2. So the correct answer to question 1 is choice B. Now let's take a look at question 2. Question 2 says, which of the following will produce the greatest mass of CO2 when it undergoes complete combustion with O2? Let's take a look at choice A. Choice A says 100 grams of CH4. So what I'm going to do is write a balanced chemical equation for the complete combustion of CH4. So CH4 reacts with O2 to produce carbon dioxide and water, so CO2 and H2O. This is an unbalanced chemical equation. So I see 4 hydrogen atoms on the left, so I will put a 2 in front of the H2O to balance the hydrogen atoms. Now I see a total of 4 oxygen atoms on the right, so I will put a 2 in front of the O2. Now I'm going to write 3 additional balanced chemical equations for the complete combustion of the compounds in choices B, C, and D. So in choice B, we have a compound C2H6. So that reacts with O2 to produce CO2 and H2O. I will balance the carbon atoms by putting a 2 in front of the CO2. I will balance the hydrogen atoms by putting a 3 in front of the H2O. Now I see a total of 7 oxygen atoms on the right, so I will put 3.5 or 7 halves in front of the O2. Moving on to choice C, the compound is C3H8. So I will first balance the carbon atoms by putting a 3 in front of the CO2. I will balance the hydrogen atoms by putting a 4 in front of the H2O. And now I see a total of 10 oxygen atoms on the right, so I will put a 5 in front of the O2. And then the last compound in choice D is C4H10O2. So I'll balance the carbon atoms by putting a 4 in front of the CO2. I will balance the hydrogen atoms by putting a 5 in front of the H2O. And I see a total of 13 oxygen atoms on the right. There's already 2 oxygen atoms in the compound that was burned or reacting with oxygen, so I need 11 oxygen atoms, because 11 plus 2 is 13. So I will put 5.5 or 11 halves in front of the O2. Now at this point, You might think that this is going to be a complicated process for answering this question because we have to convert grams of each chemical into grams of CO2. There's actually a much easier way to solve this problem, but I wanted to show you all four of these balanced chemical equations to show you what they have in common. So I'm going to highlight the CO2 on the right side of the equation. In each of these chemical equations, the carbon dioxide, the CO2, came from the carbon atoms that were consumed in these chemical reactions. So which of the following will produce the greatest mass of CO2 is what I'm trying to answer. But the carbon atoms in each sample are converted into carbon dioxide in all four of these chemical equations. So the sample that contains the greatest number of carbon atoms will produce the greatest amount of CO2. So the simple way to answer this question is to focus on the following. Which of these samples contains the greatest number of carbon atoms? And so a good first step is to convert from grams to moles. So let's start with choice A. We have 100 grams of CH4. I would like to convert this from grams to moles. So using the information on the periodic table, the molar mass of CH4 is equal to 16.042 grams per mole. When I pick up my calculator and do 100 divided by 16.042, I get approximately 6.2. That's 6.2 moles of CH4, which would correspond to 6.2 moles of carbon atoms. Now let's move on to choice B. We have 200 grams of C2H6. Using the information on the periodic table, the molar mass of C2H6 is 30.068 grams per mole. Now, after I convert from grams to moles, I have to recognize something important about the chemical formula, C2H6. There is a subscript of 2 for the carbon atom. So that means that there are 2 moles of carbon for every 1 mole of C2H6. So now when I pick up my calculator and do 200 divided by 30.068 times 2, I get a value of approximately 13.3 moles of carbon. Remember, the sample that contains the greatest number of carbon atoms will produce the greatest amount of CO2 in a complete combustion reaction. And since 13.3 is greater than 6.2, I can already eliminate choice A. Now let's take a look at choice C. We have 300 grams of C3H8. Using the information on the periodic table, the molar mass of C3H8 is 44.094 grams per mole. And after I convert from grams to moles, again, I have to recognize that there is a subscript of 3 in the chemical formula for C3H8. That means that there are 3 moles of carbon atoms for every 1 mole of C3H8. When I pick up my calculator and do 300 divided by 44.094 times 3, I get a value of approximately 20.4 moles of carbon. Again, the sample that contains the greatest number of carbon atoms will produce the greatest amount of CO2 in a complete combustion reaction. Since 20.4 is greater than 13.3, I can eliminate choice B. And then finally, let's move on to choice D. We have 400 grams of C4H10O2. Using the information on the periodic table, the molar mass of C4H10O2 is equal to 90.12 grams per mole. Again, paying attention to that subscript. In this particular chemical formula, there is a 4 as a subscript for carbon, which means that there are 4 moles of carbon for every 1 mole of C4H10O2. So I pick up my calculator and do 400 divided by 90.12 times 4, and I get a value of 17.8, which is less than 20.4. So I can eliminate choice D. So the correct answer to question 2 is choice C. And the strategy that we used to figure out the correct answer is the sample that contains the greatest number of carbon atoms will produce the greatest amount of CO2. Now, let's take a look at question 3. Question 3 says hexane C6H14 undergoes combustion with O2 according to the equation above. In a certain experiment, 12 moles of C6H14 reacts with 95 moles of O2 until one of the reactants is completely consumed. Which of the following statements is correct? Now, in my earlier video on topic 4.5, which covers stoichiometry, I presented two different strategies for determining the identity of the limiting reactant. In one strategy, you compare how much reactant is needed with how much reactant is available. In the other strategy, you calculate the theoretical yield of product starting from each reactant. If you look at the four choices in question 3, they all feature a limiting reactant as well as how much H2O is formed. So since we're focusing on the theoretical yield of H2O, we're going to use this strategy to calculate the theoretical yield of product starting from each reactant. So in this problem, we have 12 moles of C6H14 and we have 95 moles of O2. Let's convert each of these reactants into H2O to identify the limiting reactant. So I'll start with C6H14. Looking at the coefficients in the balanced chemical equation, we can see that 14 moles of H2O are produced for every 2 moles of C6H14 that are consumed. And if I pick up my calculator and do 12 times 14 divided by 2, I get a value of 84 moles of H2O that are produced. Now I have to repeat that process starting with 95 moles of O2. So looking at the coefficients in the balanced chemical equation, I see that 14 moles of H2O are produced for every 19 moles of O2 that are consumed. I pick up my calculator and do 95 times 14 divided by 19, and I get a value of 70 moles of H2O. So now I have enough information to answer question 3. I can see that 70 is less than 84. So this tells me that the limiting reactant in this problem is O2 because it leads to a smaller amount of the product, H2O, in the stoichiometry calculations. And the theoretical yield of H2O produced is 70 moles of H2O. So the correct answer to question 3 is choice C. O2 is the limiting reactant and 70 moles of H2O is formed. Now, let's take a look at question 4. Question 4 says when 6.00 grams of KClO3 undergoes decomposition according to the equation above, 2.00 grams of O2 is produced. What is the percent yield of O2 in this experiment? The equation for calculating the percent yield is actual yield divided by theoretical yield times 100. And we are given in this problem that 2.00 grams of O2 is produced. So that is the actual yield. What we need to calculate in this problem is the theoretical yield of O2. So to calculate the theoretical yield of O2, let's start with 6.00 grams of KClO3. So 6.00 grams of KClO3 is going to be converted into grams of O2. The first step is to go from grams to moles. So using the information on the periodic table, the molar mass of KClO3 is 122.55 grams per mole. So that is our first conversion factor to go from grams of KClO3 into moles of KClO3. Now we use the equation coefficients, and there are 3 moles of O2 produced for every 2 moles of KClO3 consumed. And our final step is to go from moles of O2 to grams of O2. Again, using the information on the periodic table, we see that the molar mass of O2 is 32 grams per mole. So now we pick up our calculator and we do 6 divided by 122.55 times 3 divided by 2 times 32. And this will give us the theoretical yield of O2 that should be produced in this experiment. And so that works out to be 2.35 grams of O2. That is our theoretical yield. Now what we have to do is pick up our calculator and do 2 divided by 2.35 times 100. And we get a value of 85.1% yield. So the correct answer to question 4 is choice D. Now, let's take a look at question 5. Question 5 says a student adds an excess amount of aqueous AgNO3, silver nitrate, to a 50.0 milliliter sample of aqueous CaCl2, calcium chloride, of unknown concentration. A precipitate of solid silver chloride is formed according to the equation above. If 5.73 grams of solid silver chloride is formed in this experiment, what is the approximate concentration of calcium chloride in the original unknown solution? So we are told that the student adds an excess amount of aqueous silver nitrate. If silver nitrate is the excess reactant, then calcium chloride is the limiting reactant. The limiting reactant is completely consumed in this experiment. So in this reaction, all of the calcium chloride is converted into the products, which are aqueous calcium nitrate and solid silver chloride. So we know that a precipitate of solid silver chloride is formed, and we know the mass is 5.73 grams. So a good first step in this problem is to take 5.73 grams of silver chloride and convert that into moles. So using the information on the periodic table, the molar mass of silver chloride is 143.32 grams per mole. So we'll convert grams of silver chloride into moles of silver chloride. Now we're trying to determine the concentration of calcium chloride in the original unknown solution, so let's use the coefficients from the balanced chemical equation to convert moles of silver chloride into moles of calcium chloride. And so based on these coefficients, we see that for every 1 mole of calcium chloride that is consumed, 2 moles of silver chloride are produced. If we stop right now and do this calculation, it would be pick up your calculator and do 5.73 divided by 143.32 divided by 2, and we get an answer of 0.0200 moles of calcium chloride. Now at this point, you might think that the correct answer to question 5 is choice A, but if you look carefully at the units, what we have just calculated is moles, not molarity. So the correct answer is not choice A. So how do we get molarity? Well, the definition of molarity is moles per liter, moles of solute per liters of solution. And we know that we have a solution of unknown concentration that has a volume of 50.0 milliliters. So to do this calculation, let's convert milliliters into liters. So 50.0 milliliters times 1 liter over 1,000 milliliters, that gives us a volume of 0.0500 liters of solution. So our final step to determine the correct answer to question 5 is to calculate the molarity of the calcium chloride. That would be 0.02 divided by 0.05. And this gives us a value of 0.4 moles per liter. So the correct answer to question 5 is choice B. Now let's take a look at question 6. Question 6 says a student dissolved a sample of oxalic acid, H2C2O4, in water in an Erlenmeyer flask. Then the student titrated the oxalic acid solution in the flask with a solution of aqueous KMNO4, which is called potassium permanganate, in a burette. The chemical equation for the reaction that occurred during the titration is shown above. The volume of 0.0250 molar aqueous potassium permanganate required to reach the end point of the titration was 19.20 milliliters. How many moles of oxalic acid were present in the flask? So a good place to start in this problem is the fact that we are given both a volume and a molarity of this aqueous KMNO4 solution, the potassium permanganate. And if we know the volume and the molarity, we can calculate the number of moles of that substance. So the volume is 19.20 milliliters. First, let's convert the units of milliliters into liters. So there is 1 liter for every 1,000 milliliters. And then that capital M, that represents molarity or moles per liter. So 0.0250, capital M, that means 0.0250 moles of the potassium permanganate for every 1 liter. Now, if you look at the balanced chemical equation, you'll notice that it says MnO4 minus on the left side of the equation. That's the permanganate ion. So for every 1 mole of potassium permanganate, KMNO4, there's 1 mole of the permanganate ion. So I'm just showing you that as a conversion factor to go from moles of potassium permanganate to moles of the permanganate ion. Now, it says in this problem, the last sentence is, how many moles of oxalic acid, H2C2O4, were present in the flask? Let's use the coefficients from the balanced chemical equation to convert from moles of MnO4 minus, permanganate, into moles of oxalic acid, H2C2O4. So looking at the coefficients, 5 moles of oxalic acid are consumed for every 2 moles of the permanganate ion. Now I'm going to pick up my calculator and start from left to right and do 19.20 divided by 1,000 times 0.0250 times 5 divided by 2. And if I do that math, I will get the number of moles of oxalic acid that were present in the flask. So this calculation gives me a value of 0.0012 on my calculator, which, if I write that in scientific notation, would be 1.2 times 10 to the negative 3 moles of oxalic acid. So the correct answer to question 6 is choice C. Now, let's take a look at question 7. Question 7 says a 50.0 milliliter sample of an acid, HA, of unknown molarity is titrated with NaOH, which is sodium hydroxide. The pH of the resulting solution is measured with a pH meter and graphed as a function of the volume of 0.200 molar sodium hydroxide added. The titration curve is shown below. Now, we are not given a balanced chemical equation for the acid-base reaction that occurs in this titration experiment, but it's a very simple balanced chemical equation. We have an acid, HA, we have a base, NaOH, and when the acid and the base react together, they produce water and they produce an ionic compound or a salt. So it's important to understand that in this very simple acid-base reaction, there is a 1-to-1 mole ratio between the acid, HA, and the base, sodium hydroxide. So that 1-to-1 mole ratio will be important when we do our calculations to answer question 7. Now, I'm going to show you on this slide, this is information that I had presented in an earlier video when I talked about topic 4.6, Introduction to Titration. Take a look at that last bullet point on this slide that I'm highlighting. It says, in an acid-base titration, the pH of the solution in the flask can be monitored during the experiment. the pH data can be used to create a titration curve. The pH is usually plotted on the y-axis, and the volume of the titrant added is plotted on the x-axis. The equivalence point of the acid-base titration occurs when there is a rapid change in pH. Now let's take a look at the titration curve for the diagram that was given in question 7. And you can see that there's a rapid change in pH that occurs after 45 milliliters of the titrant has been added. So that number, 45 milliliters, is going to be used in our calculation to determine the concentration of the acid solution. Remember that molarity is moles per liter, so let's first convert milliliters into liters. So for every 1 liter, there's 1,000 milliliters. We are given both in the description of this sodium hydroxide solution as well as the x-axis label that the concentration of sodium hydroxide is 0.200 moles per liter. So there's 0.200 moles of sodium hydroxide for every 1 liter. And as I mentioned earlier, there's a 1-to-1 mole ratio between the acid HA and the base sodium hydroxide. So if I pick up my calculator and do this math, which would be 45 divided by 1,000 times 0.200, I would get the number of moles of the acid that were present in the solution that was titrated in this experiment. And so when I do that math, I get 0.0090 moles of the unknown acid. Now at this point, that is not molarity, that is just moles. Let's take a look at the description in question 7. It said that the volume of the acid was 50.0 milliliters. Remember that when you convert from milliliters to liters, you divide by 1,000. So 50 divided by 1,000 would be 0.05. Molarity is moles per liter. So we've already calculated the number of moles of the acid, which is 0.0090 moles of the acid, HA, divided by 0.500 liters of the solution that was titrated. And when I do that math, I get 0.18 moles per liter. Now take a look at the 4 choices, A, B, C, and D. We have words such as slightly less than or slightly more than, and then we have 2 concentrations. So we know that if we use a pH meter, we should get a concentration of 0.18 moles per liter. So I'm going to eliminate choices C and D because they have the wrong concentration of the acid solution. Now I have to determine whether or not, based on the information in this experiment, if the calculated concentration of the acid will be slightly less than 0.18 moles per liter or slightly more than 0.18 moles per liter. So it says a student carries out the same titration but uses an indicator instead of a pH meter. And if the indicator changes color slightly past the equivalence point, what will the student obtain for the calculated concentration of the acid? I'm going to go back to that slide that I showed you earlier. This was the summary of the details related to a titration experiment. Again, that would be from topic 4.6, Introduction to Titration. And so take a look at the highlighted bullet points on this slide. The equivalence point is reached when one reactant has reacted completely with the other reactant according to the stoichiometry of the chemical equation. An indicator can be used that will change color to give a signal when the equivalence point is reached, and the end point is an observation, such as a color change, that indicates when to stop adding the titrant. The final volume on the burette should be recorded. So if the indicator changes color slightly past the equivalence point, let's say instead of 45 milliliters, the student stops the titration after 46 milliliters of the titrant were added. Now, obviously 46 is a little bit higher than 45, so if I were to run these calculations, instead of getting 0.009, I would get something like 0.0092, which again is slightly larger than what I had earlier. So now when I do the calculations for the concentration of the acid, you can see that I'm going to get a number that is slightly more than 0.18 moles per liter. So the correct answer to question 7 is B, slightly more than 0.18 moles per liter. Now let's take a look at question 8. As you can see, question 8 also involves an acid-base titration experiment, and it involves the appearance of a titration curve. So question 8 says, the reaction between acetic acid, HC2H3O2, and potassium hydroxide, KOH, is represented by the equation shown above. A student titrates 20 milliliters of 0.200 molar acetic acid with 0.160 molar potassium hydroxide using a probe to monitor the pH of the solution. The data are plotted, producing the following titration curve. Then the question goes on to say that a second student titrates 20 milliliters of 0.100 molar acetic acid with 0.160 molar potassium hydroxide. Which of the following diagrams is most likely to represent the titration curve from the second student's titration? Let's compare the details of the first student's titration with the second student's titration. So we're not changing the volume of the acid. We're not changing the concentration of the potassium hydroxide. The only difference is that we are cutting the molarity or the concentration of the acetic acid in half. You can see we go from 0.200 moles per liter to 0.100 moles per liter. So what does that mean for the appearance of the titration curve? Well, if you start with half the number of moles of acid, then you will need half the number of moles of base to reach the equivalence point. And so right now on this titration curve, the equivalence point is reached at a volume of 25 milliliters. In other words, it takes 25 milliliters of the potassium hydroxide, which is the titrant, to reach the equivalence point. And since half of 25 is 12.5, we would expect that rapid change in pH to occur at this point, so the titration curve would look something like this. So we're looking for a titration curve in which the rapid change in pH would occur at around 12.5 milliliters. So the correct answer to question 8 is choice A. Now let's take a look at question 9. In question 9, we're still talking about an acid-base titration experiment, but what makes question 9 a little different is that we're calculating the molar mass of an unknown acid. So question 9 says, a chemist performed a titration experiment in order to determine the molar mass of an acidic substance HX. The chemist dissolved a 1.40 gram sample of solid HX in water and added a few drops of an acid-base indicator to the solution to ensure visual detection of the endpoint. The chemist titrated the aqueous HX solution with aqueous NaOH, which is sodium hydroxide. The chemical equation for the reaction that occurred during the titration is shown above. The volume of 0.500 molar sodium hydroxide required to reach the end point of the titration was 22.95 milliliters. What is the approximate value for the molar mass of HX? So a good place for us to start our calculations for question 9 are the fact that we have both a volume and a molarity of this sodium hydroxide solution. So when you know both the volume and the molarity, you can calculate the number of moles. So we have 22.95 milliliters of this sodium hydroxide solution. First, I'm going to convert from milliliters to liters, so times 1 liter over 1,000 milliliters. 0.500, capital M, means 0.500 moles of sodium hydroxide for every 1 liter. if I look at the balanced chemical equation between the acid, HX, and the base, NaOH, I can see that there's a 1-to-1 mole ratio between the sodium hydroxide and this unknown acid, HX. So 1 mole of HX for every 1 mole of NaOH. Now, if I do this calculation, this won't give me the molar mass, but it will give me the number of moles of this acidic substance, HX, that was used in the titration experiment. So I'll pick up my calculator and do 22.95 divided by 1,000 times 0.5, and on my calculator I get 0.0115 moles of the acidic substance HX. Now, the only other piece of data or measurement that I haven't used yet, which I'm going to use to get the final answer for question 9, is it says the chemist dissolved a 1.40 gram sample of solid HX in water. So 1.40 grams divided by the number of moles, 0.0115 moles, that will give me units of grams per mole. And those are the units for molar mass. So looking at my 4 choices, A, B, C, and D, the correct answer is going to be what I get on my calculator when I do 1.4 divided by 0.0115. And since I get a value of 122 grams per mole on my calculator, that means that the correct answer to question 9 is choice C. So question 9 is the last question in this packet. I hope that you found all of these answers and explanations helpful. Thanks for watching.